So in this lecture we're going to talk about gravitational potential. And it's given the symbol capital V subscript little g. And can anyone remember the definition of electric potential difference, which was V equals something? If I had an electric field and had a charge Q, and I wanted to move it from a point A to a point B, electric potential was the work done in moving that charge across the field per unit charge. Right? So can anyone take a guess at what the definition of gravitational potential is going to be like? Moving from charges to masses. Yep. Right, it's going to be the work done in moving a mass within a gravitational field per unit mass. Okay, and there's a more exact definition if you like. So the gravitational potential at a point P in a gravitational field is the work done per unit mass in bringing a small point mass m from infinity to the points P. Can anyone guess the units? What's the units of work? Joules. What's the units of mass? Kilograms. Joules per kilogram. So that's the definition, if you like. But we, in a previous lecture, just found out that there is an expression for the work done, gravitational, in moving a mass from infinity to P, so we can use that. So if I start from gravitational potential is work done per unit mass, then the work done is none other than the gravitational potential energy for moving a point mass from infinity to the point. So this was which was equal to minus big G m little m over r. And then we have to divide everything by little m. So we notice that the little m's cancel. So it has nothing to do with we assume here that we have a small point mass, otherwise this doesn't hold so well. And we end up with gravitational potential equals minus big G m over r. And note, however, though, this is a scalar quantity, so we have no direction, unlike with gravitational field strength, which was a vector quantity. If we look at this thing up here, then the work done, or the gravitational potential is the work done over mass. If I multiply both sides by mass, then I get, so in general, the work done is equal to the mass times the gravitational potential, and the work done is the same as the change in gravitational potential energy. And I believe this is in your data booklets. What's really important to note, though, is if I have let's draw it up here. Here's my big mass m. Here's my small point mass little m, starting out at a point A over here, and it's going to end up at a point B, say over here. Then the work I do on little m is independent of the path I take. I could follow this path, or I could follow this path, or I could go straight across here. The work done would still be the same, so it's path independent. However, we do assume, though, that I do this slowly. Why do you think we have to assume that when I move the point mass, I do it slowly? What other type of energy would I be converting to if I do it speedily? Kinetic, right? So we don't want to use up kinetic energy.